Okay, so the title here is what was the Roswell Memory Foil made of? This is a work that I started on probably about 15 years ago when I was in a whole series of discussions with various people online, and everybody was trying to sort of come up with ad hoc explanations, about the memory foil. And so I decided to try to take a systematic approach, and kind of in each case dig down to sort of physical principles and see if there was a coherent story that emerged. So briefly, the outline here is that if you look at the body of all of the witness reports of the Roswell Memory Foil, there's approximately 24 of them out there, on the internet in various publications that have accumulated over the years. And then, of course, there are individuals such as myself and Jack, and I would guess others on this call that have their own individual witnesses that they know of and that are not public. So there seems to be. So the bottom line is there seems to be a number of people out there who are all telling kind of similar or slightly different versions of the same story. So the point here is to look at each of and there's 6 main characteristics of the memory foil that have been reported. I'm going to look at each one of them individually. And the first question to ask is, for that particular characteristic, are any of those not explainable by conventional physics? If any are, then the next step is, well, what is kind of the minimum physical principle that you would have to invoke in order to explain that? It's kind of just Occam's razor. What's the sort of minimum new explanation that would be needed? And then once you go through that, for each of the 6 characteristics, you can then go back after the fact and ask the question, well, if you did need to invoke some new physics to explain some particular characteristic, is that consistent with all the other characteristics? Would that negate some other explanation? And if you go through that process and the answer is no, it's all consistent, then you've got at least the beginnings of a story that could explain this set of characteristics. And if you do, then you can then attempt to match that to some kind of theoretical model for what's going on. To fast forward, that's the approach I've taken, and I suggest that there is in fact a need to invoke a novel physical principle, and I'm going to propose a model to address that. Okay, so I guess I won't spend much time on the sort of the origin story of this memory foil. I'm going to assume that everybody knows that to at least some extent, that the bulk of the stories originate from the July 1947 incident that happened at the Roswell Army Air Force Base, and as a result of that, some 22 different witnesses over the years have come forward and told their little part of the story. Various researchers in this field have compiled that list, and you can, in the written talk here, you can get pointers to that if you're interested. Most of those stories were collected in the 80s and 90s, when the story sort of first became big in the popular mind, and there were a number of books written and so forth. but there's been at least one additional case that I find very interesting, which has only surfaced in probably since about 2016. And I will just briefly mention that one. In this particular case, there are these two children. One, they in this case, they're going by pseudonyms Jill and John. And Jill was 10 years old at the time, and John was 8 years old at the time. And they both lived in a little community called Page Manor in Ohio, which is a suburb of the Wright-Patterson Air Force Base. And the year was 1957. Now, I mean, they're literally just across the fence from the main runway and at Wright-Patterson. The girl's father was a major in the Air Force, and he was a pilot in the Tactical Air Command, stationed there. The boy's father was a colonel, and he was apparently an engineer and a scientist in what looks to be the Foreign Technology Division, which was located on the more secret side of the air base there. One day, the boy borrowed a piece of some mystery material out of his father's home office and brought it to school one day to show to Jill, and said, you know, after school, let's go and, you know, play with this stuff. It was described as, again, a thin foil-like material, described as about 8.5 by 11, you know, roughly a standard, you know, piece of paper. And one of the things that makes this story interesting is that they got to play with it for about a week or so before John's father noticed that it was missing and came back and reclaimed it. So unlike many of the other witnesses, most of whom only saw the material or had access to it for a few minutes, these two kids apparently had it for, you know, 5 or 6 days and were able to actually try a number of different experiments with it over that period of time. And they pretty much described what we see in a lot of the other reports, that you could crumple it up and, you know, throw it through the air and it would spontaneously go back to its shape, or you could crumple it up and lay it on a table and it would instantly go back flat with no, you know, permanent creases or anything like that. Seemed to be very strong. You know, they would pound on it with hammers, try to cut it with scissors and knives, no effect. Put it under the wheels of a big heavy truck, you know, nothing. Subjected it to high temperatures. In the neighborhood where they lived, there was a gentleman who was who ran he was a farrier, which, for those of you who are not familiar, that's the guy a blacksmith who makes horseshoes and stuff like that. And he had a forge, you know, a typical coal-fired forge, and they would put the material in there. Again, no melting, no heating, no glowing or anything like that. But the one observation that really kind of sets this report apart is that the girl on kind of the last day that she had access to this material had placed it in the basket on her bicycle and was riding across a parking lot. And this was late evening, and it was you know, dark, but there were street lights illuminating this parking lot. And she reported that when she got when this piece of material was directed in a certain direction to the street light, the light appeared to, as she described it, enter the foil and, you know, basically transfer along the surface of it and exit at the edge that was closest to her. And so it lit up, you know, basically like my interpretation of that, it was was essentially acting as a waveguide to the incident light, and translating across the surface of it. And so it lit up, and she never ever seen anything like that before, and it totally fascinated her. And so that's the interesting part of that one. Okay, so if you look at the basic characteristics, there's 6 of them that I've identified, and I've kind of assembled them in order of ascending strangeness. The first one, everybody agreed that it was a metallic appearance. Typically, gunmetal gray would be the descriptor that they would use. Everybody described it as lightweight, or technically, low density. Everybody described it as having high strength. Couldn't cut it, couldn't crush it, couldn't, people shot it literally with a 30-06 rifle, wouldn't penetrate it. And no one had ever seen that before. The 5th one is the one I just mentioned. It seemed to be optically active. It was not simply a monolithic piece of metal or something that just reflected, or just obeyed, reflection principles. And the 6th one, which I think is actually the most interesting, was this extreme heat resistance. Okay, so just kind of briefly, let's go through what is metallic appearance. Well, it's basically a shiny, lustrous surface coupled with high opacity. So, if you shine a light on it and look at the other side, the light won't come through. And it can be, it can only be like a sheet of aluminum foil, will do that. Well, so where does that come from? Well, ultimately, those appearance qualities of metals come from the fact that the metals are modeled as the so-called electron C model, where you have the core atoms of the metal, whatever it might be, aluminum or iron or whatever, are bound together, strongly in a matrix, an ordered matrix. But the outer valence electrons are not highly bound to those atoms, and so they're able to kind of float around in a non-localized manner, not attached to any specific item. So they form this sea of electrons that are kind of floating around against this background of the matrix. As such, that those electrons in the sea are able to absorb and re-emit wavelengths of almost all sizes. They're not bound by strict quantum transitions, and so you get this ability to absorb and reflect basically all wavelengths, so it looks shiny. Also, when a photon is absorbed, it of course can reflect back out, but it can also emit back into the body of the metal. And again, since you have this electron sea, they're all absorbed, dissipated, and so a light wave can't make it very far through the body of it. So that's basically why you get the shiny, lustrous surface and opacity. And so, so the simplest explanation for the memory foil is that it simply had a metallic component. So no new physics required, not very mysterious. Okay, now let's look at the low density. One witness actually reported seeing, bits of the memory foil floating on puddles, little puddles of water after rainstorms that had occurred out in the debris field for weeks or months after the actual, event. So that implies that the material, the density of the material was somewhere in the vicinity of 1.0. If there were no other considerations, you would say, well, okay, the fact that it's floating on water means obviously its density is somewhat less than water. But you can have other effects that come into play. For example, if the material was hydrophobic, it could actually float on the water and still be slightly more dense than water. You can see this with things like these water striding insects that can, you know, float on the surface tension layer. And those effects can be additive. But the net result is that that tells us that the density is probably around 1.0 plus or minus a little bit. So there are really only 3 metals that are actually less dense than water: lithium, potassium, and sodium. They're all highly reactive, so that, you know, that certainly wouldn't explain it. The other thing is you can actually have voids within a material, right? I mean, if you take a piece of like foam or woven fabric made out of some material, the bulk density will actually be less than the density of whatever that specific material is, because you've got these voids in there, and if you average it over the total volume, it can actually be less dense than water, even though the parent metal that it might have been made from can be more dense, right? So, and by the way, some of the witnesses claimed that the so-called foil actually had a fabric-like structure. They claim that when you looked at it under magnification, it looked more like a woven material with very, very fine, fibers than it did just a simple monolithic material. Upshot of that is there's no new physics or anything required to really understand the low density and why it could float on water. Okay, high strength. Well, as I said, one set of witnesses reported shooting at the foil with a 30-06 rifle, which is a very high-powered rifle, and basically the foil would just spin up in the air and fall down, and they would inspect it, and there was no marks or damage or anything like that. Well, so that kind of behavior has actually been observed with like silk fabric or Kevlar fabric for other projectiles that are probably not as high velocity as a 30-06. So that characteristic by itself is not that mysterious, although in my estimation, the fabric to have done all the things that these witnesses claim, I think the material would have to be maybe a factor of 2 or so stronger than, let's say, Kevlar. Not infinitely stronger, not by a huge amount, because things like Kevlar and other high tensile strength metals even can exhibit this behavior of being very difficult to cut with scissors or a knife or something like that. So as we're discovering, having materials that are like maybe a factor of 2 stronger than let's say Kevlar is totally within the realm of theoretical possibility, and we're making progress on this kind of all the time. For example, nano-engineered sandwich materials where you have different metals and so forth can achieve that kind of strength, right? And these are being engineered and experimented with all the time. Now, obviously that wasn't available in 1947 just because of the technology. We didn't know how to do it. But I would say that there's no new physics required to explain that if you had the technology to actually implement it. Okay, now let's get to the shape memory. This is the characteristic that everybody kind of concentrates on. And I argue that it's actually, in many ways, it's, again, one of the least interesting or mysterious parts of the whole thing. If you look at the witness testimony, I assert that there are basically two different processes or different parts of that shape memory that were reported. One component of that story is that whenever you would crumple the stuff up tightly and allow it to re-expand, it would leave no permanent creases or wrinkles in it. So that's one observation. The other observation was that not only would it have no permanent creases, but it would almost instantaneously flow back. Witnesses often use that term, the flow back into its original shape, even if you like placed it on a table or threw it through the air or something like that. I believe that those two processes point to two different physical effects. And I'll get to that shortly here. So the first thing to recognize that every solid material has shape memory to some extent. That's simply a reflection of Hooke's law, which basically says that if you take a piece of material and you apply a set of forces or stresses on it, the material will deform, and that deformation is measured as strain or change of shape. And that for any particular material, there's a constant, the elastic modulus, that explains how much distortion you get for a given amount of force or stress that you put on it. And so, so basically all it says is that if you take a piece of material, put a set of forces on it, it'll distort and it'll change shape, and you remove that set of forces and it'll go back to its original shape. Well, that's shape memory. The trick is that there's a couple things about that. One is that's only true if the amount of stress that you put on it and the amount of strain that it experiences does not exceed a certain threshold value, which is called the yield strength, or the yield strain of that material. If you apply a force that's greater, that causes an amount of distortion that's greater than that threshold value, one of two things will happen. One is it'll, excuse me, the material will take a permanent step. It'll stay in a, excuse me, in a distorted condition, so it won't return to its initial shape, or it'll break. Or if you do it long enough, both of those will happen, right? So that this linear relation between forces and distortion only applies as long as the amount of distortion is within the elastic limit. It's called the elastic limit of that material. So I looked at how much strain, how much distortion would you get if you took, let's say, a flat piece of thin foil and folded it back on itself, and obviously that if you fold it back on itself, and this is what you could see if I had the slides up here, you'll have like one piece of flat material and a bend, and then another piece of flat material where it's bent back over itself, and there will be a certain radius or diameter of that bend. Okay, so what happens if you just keep making that bend diameter smaller and smaller and smaller? Eventually, you get to the point where the top piece of the foil is lying on the bottom piece of the foil, and the diameter of that fold is basically the thickness of the material itself. And you can show mathematically that when you get to that condition, the amount of strain, the amount of distortion that you would have in that fold is like 100%. Okay, so the question is, well, what is the elastic limit for common materials? Well, most metals like aluminum, iron, brass, what have you, have a limiting strain of like less than 1%, right? So you don't, I mean, you can do, you take a paper clip or something and you can bend it just a tiny amount and it'll stay bent, right? Plastics like acrylics and so forth can have an elastic limit of maybe a couple of percent. So they're actually quite a bit more flexible than most metals, but even so, 2% is not a whole lot. Exceptional metals like nitinol was often proposed as an explanation. They have an elastic limit of maybe 5 or 6%. So still not even close to what you would need to be able to fold something up into tight fold and then have no permanent creases in there. So are there any materials that have a high elastic limit, greater than 100%? Well, yes, rubber is, latex rubber is the most common one. You can take a rubber band and stretch it to within to maybe 500% of its original length, and it'll return to its original length. It won't do it instantly, by the way, but it'll return to its original shape and size with no permanent deformations. So really, there's no new physics required to explain the superelasticity either. All you need is a material that has an elastic limit that's greater than about 100%. I don't know of any others than rubber, by the way. So there's no new physics required to explain that, but I don't know of any materials that existed in 1947 or even today that have this high strength and the high and the metallic appearance that would do that. But now let's get to the other element of the whole shape memory thing, which is that many witnesses describe that they would crumple this stuff up, put it on a flat like the table, and it would just instantly flow back to its original position. Well, a piece of material like the thin rubber sheet won't do that, and the reason is because gravity will hold pieces of it together. The only restoring force in a piece like that is the fact that the rubber itself is bent over, and so right at the bend you'll have elastic forces that want to restore it to its original shape, but you have the other piece lying on top of the other piece that resists that, and that friction between the two sheet, the upper and the lower sheet, prevents it from kind of like instantaneously flowing back to its original shape. So I believe that there has to be another set of forces that I think are basically surface forces on the foil that would allow it to essentially flow over itself and flow back to its original shape and do that quickly. So that to me is the first indication that there might be some physics here that are not entirely explained. Okay, then we have this optical waveguide part. It seems to me there are two sort of categories of possible explanations there. one possibility is, maybe it was a hyperbolic metamaterial waveguide that can support surface electromagnetic waves. That might explain it. The other alternative, it looks to me, is that there was simply maybe an index of refraction gradient near the surface of the foil, which could also, bend the light rays and perhaps cause them to transit parallel to the surface instead of getting reflected. Either one of those explanations is understandable now. In 1947, I don't think people were really thinking about nanomaterial, metamaterial waveguides, but certainly, a gradient in the index of refraction was known. That's basically, things like optical fibers and so forth. Obviously, neither one of those explanations was consistent with 1947 technology, but I believe that we could understand the science of them from our current perspective. And so at this point, I can't really make a choice between those. Okay, so now let's finally get to what I think is the good one, the heat resistance. There were many, or several witnesses who over the time basically had exposed the material to things like a kitchen stove, a natural gas flame, and a couple of them even claimed to have exposed this to an oxyacetylene torch. So an oxyacetylene torch has a flame temperature of around 3000 C. There are materials that can withstand an oxyacetylene flame, not very many, by the way, but there are 5 naturally occurring elements that would, and these are basically very high density, high temperature, high Z metals like tantalum, tungsten, osmium, rhenium, and so on. Carbon, of course, can. And more recently, there are super, ultra high temperature ceramics, the kind of things that are used for ballistic missile nose tips and stuff like that. They can have melting points above 3300, C. All of those are brittle. So there are a few materials that could actually just withstand the simple high temperature, but that doesn't really explain what the witnesses were seeing, because any conventional material would still start glowing red around a little over 500 C, and by the time you got up to 3000 C, they would be glowing bright yellow or white. So a conventional material, even if it had a high melting point, does not explain why you would not see any evidence of heat at all. Why you see no glowing, no emission of light. And furthermore, a conventional material, even if you heated it up to below its melting point, would still have thermal inertia. As soon as you took the heat away, you couldn't immediately grab it and hold it without getting burned. So a simple high melting point doesn't really explain it. The second kind of explanation you might think about is, what if the foil was a thermal superconductor? Okay, well, first of all, I guess we should note that we don't have any high temperature thermal superconductors. Liquid helium can be considered to be one within certain parameters, but so what would a thermal superconductor do? Well, conventional materials require a thermal gradient between a hot spot and a cold spot in order for the heat to move from the hot to the cold, right? And this is why if you put a torch on a piece of metal or any other material like that, the hottest spot is right under where the torch flame is touching, and so that's the hottest. And in case of a oxyacetylene, that would be glowing, white hot, and then you'd get a radial, the temperature would decrease radially as you move out from that. A thermal superconductor, if they existed, would not change the fact that the material is heating up. It would simply say that all the material was heating up everywhere at the same rate and was always exactly at the same temperature. I mean, that's all it would do. But if you had a thin foil, thin piece of foil that was normal mass, normal matter, but it just simply was a superconductor, you would still be heating it up, and there would only be a certain finite amount of thermal mass there. And so if you took a small piece of this foil and hit it with an oxyacetylene torch, there would easily be enough energy there to heat the whole thing up eventually. And so again, you would see this phenomenon that it would glow, right? But it never did. And it also, again, never had any thermal inertia. You could take it right out of the acetylene flame and hold it, and there'd be no perception of heat at all. So now we get to my favorite theory, which is that the heat from the torch and these other sources, which were basically convective, heat transfer sources, never entered the material. And that would explain all of the observed phenomena. If no heat enters the material of the foil from the flame, excuse me, the foil does not heat up, it doesn't glow, it doesn't melt, and it has no elevated temperature as soon as you take it out of the flame. So to me, that's the only explanation that I've been able to come up with that explains all of the reported thermal phenomena. So how would that be possible? Well, a torch flame is basically an example of forced convection. You combust the oxygen, and in this case, the acetylene, highly energetic exothermal reaction. The reaction products are H2O and CO2 gas in an ideal oxygen hydrocarbon combustion. And those molecules, again, being polar molecules, first of all, they have high translational kinetic energy, and they also have highly excited internal states like vibrations and rotations and so forth. And then simply from the kinetic theory of gases, when those gas molecules would collide with any atoms on the surface of the material, they impart that kinetic energy, that stored kinetic energy, into the material, which then propagates through and ultimately results in heating and ultimately melting if it gets hot enough. If those gas molecules, those energetic gas molecules, never touch the surface, they never transmit that kinetic energy. By the way, I would note that this is exactly the kind of observation that Paul Hill made back in his work, published in 1995, about which he characterized as an acceleration field. Excuse me, I'm just getting over a cold here. So in his case, he looked at a rapidly moving piece of material, excuse me, which would impart kinetic energy into the gas molecules around it. We're now simply looking at the converse of that, where you have highly energetic gas molecules interacting with a solid surface, and an anti-gravitating repulsive field would stop that as well. In other words, the energy transfer would be stopped in both directions. Excuse me just a moment. So, so that's my premise, that there was an anti-gravitating repulsive field near the surface of the foil. It would and it would explain the highly anomalous thermal behavior of the foil. It might also actually contribute to some of the other characteristics, including the low density and the high strength and the super elasticity, and maybe even the ability to act as an optical waveguide if it was in fact modifying the index of refraction right next to the surface. Okay, so now we're getting down to close to the end. So what could produce an anti-gravitating acceleration field localized right on the surface of the foil? Well, now Jack would say that obviously it was a engineered metamaterial, being pumped to create this anti-gravitating field. The problem I see with that is that the foil did not seem to have any obvious pumping, source. The foil was, presumably discovered in 1947 and handled as late as 1957. There was no obvious, power source that could have pumped it within that period of time. So if the foil was surrounded by this anti-gravitating field, it seems to be a static field and not a dynamic one. It's the DC component and not the AC component, right? So it looks to me like this could be explained if we assume the existence of negative mass matter, as discussed by Ludinger and Bondi and even Bob Forward and people like that. If it is possible to embed or attach negative mass matter to positive mass matter, then you could actually start to engineer structures in which you had a core of normal matter surrounded by a surface or a layer of negative mass matter. And the negative mass matter would be gravitationally repulsive, in all directions. Furthermore, if you had a mixture of positive mass matter and negative mass matter, that would actually reduce the apparent weight of that ensemble, because whatever the component of the negative mass matter was, when added to the positive mass matter, would go to zero, and you'd be left with a low density appearing material. So that could easily explain the low density, contribute to that. It could explain a hydrophobic surface, because it would presumably repel water molecules just as well as it would gas molecules in the atmosphere. And such a material would essentially be isolated from convective heat exchange with the atmosphere. Not necessarily radiative exchange, by the way, but convective. And then I've gone into a little sort of engineering exercise and how could you build up structures with, assuming you could have these these Bondi pairs, how could you build up structures? And I think you could do that. You know, you could build little discs, and then you could string discs together into fibers, and you could ultimately take fibers and weave them into fabrics if you wanted to, and if you were able to engineer this stuff at the atomic scale. Okay, so that's basically the end of the talk.